I would like to start talking with you about the Clean Space initiative as a whole and what you're doing in it.
So do you want me to introduce CleanSpace? CleanSpace was created in 2012.
Okay.
It was a sort of a grassroots initiative in ESA, so 2 employees. I was part of starting from bottom up, if you want, the bottom up initiative, where a few people, we were 4 in the end, signing the proposal, proposed to the Director General of the time this idea of Clean Space, so a program that would develop technologies and support system design to make sure that space activities would be sustainable and guaranteeing their future. That's a bit the idea. So it would go through all the steps of a space program, from their design and production, so all the environmental impacts on Earth.
As if it were a mission.
So we were supporting all these steps of space missions with our activities, studies, developments. So we are addressing all the development phase up to launch, and then so this part is the part that actually pollutes the Earth ecosphere, if you want. And then after launch you go into space, and then you need to comply also with certain rules to make sure you don't pollute space.
Okay.
And last but not least, trying to also compensate for previous impacts. So space is already quite polluted, as you may know. So trying to develop concepts or technologies that could help mitigating these impacts, remediate these impacts by removing debris from the environment.
So that's something that's overlapping, the part in which you deal with making new systems more sustainable and the remediation.
Yes, so there is a point of contact, let's say. It's one part of what we do, that is designing this satellite and the future satellites, not only to be already more sustainable and to be complying with the rules for space debris, but also to be ready to be removed in case they fail in orbit. So we are bringing lessons learned from what we see is difficult in removing debris that were not prepared, and we are preparing our satellites to help them a removal mission in the future in case it is needed.
And lessons learned from European agencies' missions, or?
It's from from studies, because we don't have yet the first mission. We'll have soon, I hope, but we don't have yet a mission collecting debris. But we have done intensive study on how to deal with EnviSat. That was the biggest ESA debris. We have to be clear that just by removing one debris, you're not changing the environment. But as we don't know how much funding will be put on this topic, we wanted our first mission, to have a significant impact anyway on our footprint, not on a global scale, but on our footprint. And as ESA, this was the biggest debris, so we studied a lot how to remove EnviSat. That is a fully unprepared satellite to be removed. It was designed many, many years ago. And through this process, we have learned why it's so difficult to do it, why we are not actually going for EnviSat for the first mission anymore. And this helped us saying, when we do a new satellite, maybe we should think on how to prevent all these things that are difficult about EnviSat.
Okay. For example, what? Because you mentioned the Clear Space mission. Is it?
So yes, the Clear Space mission was approved last year, and it's planned to be launched in 2024, and this would be the first mission to remove an actual debris. And that one will remove actually a launcher adapter, so a much more simple structure than a spacecraft, and also less heavy, so that should be an easier target than EnviSat. Sorry, your question was?
Why was it difficult to go with EnviSat?
So EnviSat, first of all, it is extremely heavy, so it's very hard to maneuver once you've captured it. But also, there's no physical place where to capture it. Actually, when it failed, we think it was entering its safe mode. So the solar panel actually went in front of the launcher adapter. That would be the best place to capture. So it's very hard to even capture it physically. And then also, and maybe this is one of the most difficult points, is that it started tumbling in space, and it's tumbling at more than 2 degrees per second. And this makes it really hard for a chaser to be able to cope with this. Say, if you have something turning in space like this, the chaser that comes to capture it has to start navigating around it and nullify, let's say, the relative motion. And if this satellite is moving in space too fast, it means that you're basically thrusting all the time to follow it, and depending on the accuracy of your thruster. So if you're moving fast, you need bigger thrusters. If you have bigger thrusters, your errors are bigger, so it's harder to capture. So this tumbling rate is a very important.
Okay, so you would need to follow to go in a circle around the
Yes,
and then
yes. On top of it, it is not tumbling around a single axis. It is
okay. So
tumbling
there's no
around
way
one-
just to
No,
relate
so
this
you
space
really
curve.
have to understand the tumbling motion and match it,
Okay.
which is extremely
I think
complicated.
there's something like that in the Martian movie.
Yeah,
Yeah.
that's a good example.
Yeah, right.
Yes, but if you remember well, it breaks a lot of things. Makes a lot of debris in Mars. Yes.
Right. Okay.
So we're trying to avoid that part.
And the launcher connector adapter it's not rotating. And
So
it's-
this is I don't know if you see, but in most satellites we have this round structure at the bottom that is used to connect the launcher to the satellite.
Okay.
And actually all the loads of the launch go through that interface. So that's a really stiff mechanical point, and seems ideal to dock to. Okay, but in this case, because again it was not designed with this in mind, the solar panel is deployed just in front of it, and even rotated to the worst position possible.
Yeah.
So it doesn't. So when I say preparing something to be removed, it also means you don't deploy appendages in front of the capturing point, for example. Right.
Okay. And more about the bureaucracy behind the CleanSpace project. How is it related to other parts of ESA? Because I know, for example, that a big part of the space debris office is in ESOC, Germany. Are you working together with?
Yes, a lot. So we have, say, a lot of cooperation, but the debris office is looking a lot and monitoring the space debris population.
Okay.
And also monitoring how this population is evolving over time. It's also working on the re-entry tool simulation and so on. Our nature is more, as CleanSpace is more system engineering, and is based in Aztec, so the technical center. And we actually go more in the sense of developing technologies that mitigate this, or that help a system to be demisable or to be passivated. So we are not so much into defining the consequences of non-passivated, but we are more on, okay, we need to do a passivation system. What should this look like? We need this hardware to be developed for this system to work. Okay, let's develop it. So what we do is much more linked to technology development and system development when it comes to active debris removal.
Do you do it by yourself, or are you in touch with operators, let's say?
So yes, a lot with integrators.
Okay.
So yes, that's also a part of the nature of ESA. So Aztec is working a lot more on the development phase of the satellite. So with the integrators, the designers and integrators, and the operations part is a lot linked to ESOC.
Okay. In Darmstadt.
But CleanSpace is a bit of a strange animal inside the agency, because we were created, as I said, from a bottom-up idea. We were not one of the traditional sections of the agency or units, and actually the way we were structured was, we are mostly driven by system engineers, which means that we want a certain application and then we flow down to the equipment or whatever we have to develop. So CleanSpace is really cross-cutting across the agency. So we work with all different directorates and we work with many different technical expertise, and we make the link between all of this. So we're like, a glue between a lot of different element blocks. And this is driven by the fact, for example, if we're talking about an Earth observation satellite, they will tell us we want to be prepared to be removed at the end of life, or we want to be demisable.
Okay.
But I don't think the Earth observation people want to know all that it takes to make a tank demisable. So our role is then to take this requirement from the user programs like Earth observation or telecommunications and go to the technical experts and develop the technologies that are needed for these users. So we work a little bit in a different way than it was normally done, but I think it's a very interesting process that's maybe applied in other areas in ESA in the future.
Like what? Can you?
Now we are started to work, we're still the same group, but we're starting to work on orbit manufacturing, assembly and recycling that still have this environmental part into it, but actually is much more broad than just environment. It can be a different way of doing space missions.
And why is it orbital manufacturing related to the ecosystem, let's say? Because you can launch it in pieces.
Yes, so you could launch it in pieces. Manufacturing in itself is not necessarily related to environment, but if you think recycling could be a good idea to make the space debris a resource rather than a problem.
Okay.
But something that can be interesting as well is to refurbish or do maintenance in space, in the sense that you will be able eventually to extend the lifetime of satellites, so you have to launch less. And instead of just disposing all the old satellites, you can actually reuse things that are already in orbit. And this is quite interesting because the energy and if you think about the launcher is 1,000 times heavier than what it actually launches. So if we could avoid doing all that all the time, maybe it's an interesting option also for the environment. But as I say, what I meant is that this approach, system engineering approach for technology, can also be applied in different areas that are not clean space.
Okay. And can you go into the details of the technical aspects? Like you mentioned, the demisability. What are your main concerns, technically speaking, now?
So demisability is a very complex area, and the main concerns at the moment is that we cannot yet thoroughly predict what happens during a re-entry to an equipment. We can try to, through simulations and through high enthalpy plasma internal tests and heat chambers, and we try to simulate with that the environment that the different parts will see during the re-entry of a satellite, but it's a very chaotic process and driven by many different physical processes that can be chemical reactions, can be mechanical loads, can be temperature. So to understand it and to be able to be confident about the results you're getting from simulations or from tests in order to take decisions, it's difficult. We're doing a lot of progress in the last years, but it's really a new science area. So,
and is demisability your main concern?
No, I wouldn't say so. I mean, as we are in clean space, is spread over so many different topics, but I think is within the space debris mitigation rules. So in here I include deorbiting, passivating, safe re-entry, that you don't put any risk to the ground population. I think this is the one demisability. So this is the one where we have more uncertainties at the moment and where we are learning the most.
Okay. And I have a big doubt about that because of the rise of mega constellations, we're gonna have a lot of satellites coming down, and so you mentioned previously the 1 in
10,000 is what you can
accept. I mean, with 10 satellites, that's a good number, but if we have 100,000,
Yeah.
Are we gonna challenge that number, or
It is being challenged. There are people who defend that should be per service if you want, like, or for per mission, to say not one satellite, but if your mission has 3 satellites, then the risk of your mission should be 1 to the 10, to the 10,000. At the moment, that's not the case. But it's true that the rules that are now applicable for spacecraft and for space debris mitigation, they were thought of in a very different time, in a way, or configuration of the space sector, and I think there we may need some adaptation, yes. Not only for the demise and the risk on ground, but also the probability of complying with these rules that now is requested to be 90%, but this number may become insufficient if we start multiplying the satellites in space by a very high number now of constellations.
So 0.9 probability of respecting any guidelines, or
So,
there are some that you went?
all these rules that I mentioned for deorbiting, passivate, and not
Can you maybe
causing
elaborate
ground.
on passivation?
So passivation is the process to deplete or make safe any energy that you have on board of the spacecraft when you finish your mission. So when you finish your mission, you may have some propellant on board, or your batteries may be charged, and you should try to deplete all these sources of, not sources, but all this stored energy, or put them in a safe state, so that you are sure that they will not explode afterwards. Because satellites, they can be requested to do a controlled re-entry, and then they will re-enter immediately if they are very big and put a risk on ground. But more often, they are put into a decay orbit of 25 years, and during these 25 years, they can explode and generate more debris. Or if they are in higher orbits like the geostationary ring, they will be in a graveyard orbit basically forever. So if they start exploding and generating debris, they will also put a risk to the operational missions. So passivation is quite important, and it's been driving most of the debris generation events we have seen in space, more than collisions or any other. So it is important that all missions deplete, when they finish their lifetime, that they deplete all the energy they have on board. So this is one of the requirements. Another one was, as I said, to deorbit in maximum 25 years, but if you are too big, or if you have put too much risk on ground, you should do it immediately and targeting an unpopulated area. And the last one is, if you are putting a risk on ground, you should try to limit this risk either by doing this controlled re-entry or by designing for demise. So all of this together should be done with a high probability of success. And this has been set to 0.9, so 90% probability from design, from the beginning. So you should take care also during your mission that you, because of any failure on board or so, you are not lowering your reliability at the end of life below this number, because otherwise you will put a higher risk to the environment. So this is the number at the moment, but with a lot more satellites, maybe you need a higher reliability, because if you think about a constellation of 5,000 satellites, it means still that 500 satellites could fail and stay in orbit if the 90% is hitting the bullseye. So 500 satellites more in the environment is a very important impact.
And the main concern is with respect to re-entering and being dangerous to people?
Also for space.
Even worse?
For space, I think both. But these satellites, especially the large constellations, they're small, and at the moment, as the requirement is written, that means each satellite should not put a risk higher than 1 in the 10,000. They comply, so it's not, the risk on ground is the same if they fail or they don't fail, because they will deorbit in an uncontrolled way. The thing is more if they stay in space for long, adding to the environment a high number of objects uncontrolled, is a risk for the orbits. So
And the 25 years rule is not a risk.
25 years.
Not reducing it is not a bad thing
So-
in the perspective.
When you start, if you are already put in a altitude that will make you re-enter within 25 years, this is the requirement.
Mhm.
Even if something happens after, the debris that are generated by an explosion or an impact will decay also within 25 years. So they don't add a big stress into the environment.
Mhm.
While if you leave something that stays for 200 years or 300 years, then any breakup will generate debris that will stay for very long in space,
Mhm.
and then the risk is higher. So between the 25 years or lowering it to 5 or 10 years, for me the main difference is that you may cross orbits of operational satellites or like the ISS, for example.
Mhm.
So you may try to avoid that, especially if you have thousands of satellites.
Mhm.
Because if all of those are going through the ISS orbit, it may become a risk.
So, as a general topic in environmental issues, there's a balance, I think, between individual responsibilities and systematic criticism of rules and what's going on, let's say, looking from the outside. Do you see the same applies considering the space environment, and if so, in which way?
Yeah, I think unfortunately there is a lot of parallel between space debris, environmental impacts, and other environmental impacts like global warming or so. There is always a lot of skepticism. I think human beings have a difficulty on thinking long term in a way. And if accidents are not happening now, you will say you're just being a pain and trying to impose requirements on me. Doing a mission is already so hard and expensive. Why do you force me to do anything else? So every time you're trying to prevent long-term impacts, and I think this is where I see the parallel with global warming, people tend to think that it's okay if it's another day, it's okay if it's another year, until the moment where things start to be out of control in a way. And the reality is that for both cases, we have known that they are a problem for quite a while now, and actually most of the CO2 emissions were done when we were already conscious that CO2 was a problem, and the same happens for the space debris generation. Most of them were generated when we were already conscious that this was a problem, and we didn't do much about it because we tend just to ignore, in a way, long-term risks, I think. And this is something that as a being in a race, we have to, I think, get to understand. So yes, space debris, there are also non-believers, if you want, on the fact that it is a problem, like there are for climate change. There's a lot of resistance often from industry as well, but also from agencies, because it is seen as an extra burden to be sustainable. While actually, what I think it's the case is that if we move now, or the first one moving, that they will have the burden at the beginning, but they will be also pioneering, they will also be having a competitive advantage in the future, because sooner or later these rules have to be applied everywhere. And I think it's the same with carbon. If you find good solutions and good environmental approaches, in the end you may have an advantage. I think all this process of thought, it's very similar, because I think it's very human not to care as much for what's going to happen to the next generation or in tens of years, and to always delay, let's say, the decisions until you have little option.
So you would underline the advantages of doing it now rather than talking about the danger
Yes.
of not doing it.
I think it's one of the arguments we have been using a lot. Say these rules are eventually gonna happen and be applicable everywhere, even if we are doing it earlier than others, so now we have a competitive disadvantage eventually in terms of cost. Actually, I think in the long run this will be turned into an advantage that we have done this step earlier.
How to do
Yes. And you set the rules as well. It's also something we are working a lot, not for the rules of space debris just only, but for example, to be able to do close proximity operations between two satellites in a safe way, we are trying to define how it is done. To verify design for demise, because we are in Europe doing an extra effort now and spending money on this, we're also defining how this should be verified and done. So whoever comes after most probably will have to adapt a little bit to what we have defined, because that's what becomes standard approach, let's say. So I think there is first movers advantage to be advocated, and I don't know as much about the carbon emissions, but I'm quite sure that same logic applies if you develop clean technologies for ground. They will also bring you an advantage in the near future, even if now may be seen as a burden.
And do you see, so I don't know, from my perspective, simplifying it, the public is taking care of integrating new issues in the economy or in the concerns of the people inside, and then there's the private that's thriving from those rules, trying to grow, let's say. And where do you, because you said you're a weird animal inside the public institute that it's easy. Do you see maybe a similar animal, like a private industry that can do something which is more public-like?
I think there are companies more and more that they're seeing their business model around these issues.
Because, for example, this ClearSpace will be made by ClearSpace.
So they will also be lobbying in the direction of promoting that the satellites have interfaces to be captured and so on and so forth. So yes, the moment this competitive advantage is understood also by private sector, I think they can be as good as public to promote good policies.
You're also part of the Concurrent design facility at ESTEC. Can you tell me about what that is and how is it related to cross-fertilization?
Okay, so the Concurrent design facility is a very interesting place in ESTEC because ESTEC has experts of very high level in all different subsystems and disciplines of space, spacecraft and launcher design. So what we do in the CDF is that we receive requests from what we call user programs, like I told you, Earth observation, communications, planetary exploration, whatever. They have an idea of a mission, they come to the CDF and they say, I would like to see if this mission is feasible and what this costs and what is the risk associated with it and so on. So we put together these experts from the different disciplines in the same room, and we do concurrent design sessions, and normally in about a month with 8 sessions, so two per week, we are able to tell you if it is feasible, it is not, which technologies need to be developed, how long more or less it would take to develop them, what is the cost of the whole endeavor. So it's a really effective way to have an early design and a conceptual design and an understanding of the feasibility of different missions. And actually, I brought a lot of this to CleanSpace spirits, and when I was telling you that we do this link between the customer being the user programs and then the engineers that develop the technologies is also following this sort of concurrent methodology. So it is really a place where people will discuss directly the impact. So when you take a decision on the propulsion system, it has an impact on the power system design and so on. And all these trade-offs go on live, and we analyze different options for emission very quickly. And with this we are able to to get more consensual decisions. Also the customer, so say Earth observation wants to do a satellite, they are also within the discussion. So if certain options that will get you better performance actually cost more, they can say immediately if this is a possibility or not, and we can inform them of how much it would cost more and what is the impact on schedule, and they can say if this is affordable or not. So all of this is very quick and it's done with a lot of consensus. So it's very strong methodology for early phases.
Right. And do you see also some advantage from the experts' perspective?
Yes.
Like, are they working together outside this facility or
less? So in the facility, they I think for them is also extremely valuable experience, especially they get to know or to understand better what are the impacts of their subsystem design options and the technologies they are developing, but also they get to know potential users for new ideas, so they can come up with new ideas with innovation, and they see immediately if this is applicable to the mission they're studying or not. So this is also a place for creativity.
And so you said CleanSpace came out of this?
In a way, yes. CleanSpace before...
Because you used to work in...
I worked in a CDF before.
Okay.
And then CleanSpace, actually the very first embryo of CleanSpace was a CDF study that was called EcoSat, where we said, how can we make a satellite mission more environmentally friendly? Was someone who requested. At the time I was a stagiaire, so I was just supporting the study, so it was in 2009.
Okay.
And it turned out to be very complicated, but that's when we started actually looking at methodologies for environmental assessments for the environmental impact on ground, on Earth, methodologies for complying with space debris. So basically this gave a lot of the elements that then sprout to become CleanSpace.
And can we conclude talking about the CleanSpace Industrial Days? Are you gonna organize those?
Yes, so CleanSpace Industrial Days, it's open conference, not a conference, a workshop, where we invite industry. It's very focused also on the topics of CleanSpace, and we invite industry to come and discuss all the topics that we are working on. So it happens normally every year and a half, and the next one is end of March, so in a month. And we'll be addressing all the different areas of CleanSpace. So there will be sessions on design for demise, sessions on active debris removal, sessions on orbit manufacturing, assembly and recycle, sessions on clean production on ground. So all of this will be addressed there, and I think, we had a very positive reply in terms of abstract submission, and I think it's going to be quite, the attendance is expected to be high. I just hope with the current situation, with the coronavirus, that we don't have to delay it, but fingers crossed.
Let's hope for that, and thanks a lot for your time.
Thank you. Thank you very much.
Thanks.